Welcome to this third pre-lecture video for Coordination Chemistry. The aim of this video for week 9 is to discuss some concepts in the area of organometallic chemistry. Organometallic complexes contain metal-carbon bonds and involve metal centres in low oxidation states and ligands at the very high end of the spectrochemical series which exert a very strong ligand field, such as carbonyl and phosphines. Organometallic complexes are quite distinct from Werner-type coordination complexes that we've been discussing up to this point in our course. Organometallic complexes have been known for well over a century, and their history includes milestone discoveries such as some of the complexes you can see here. Ferrocene, for example, is a particularly important sandwiched complex, named for obvious reasons because it contains iron 2+ sandwiched between two cyclopentadienyl ligands. It may not be obvious, but those suffering from diabetes often use this molecule several times a day because it's a vital part of the small electronic devices that measure blood sugar levels. The rapid growth of organometallic chemistry is often attributed to the excitement surrounding the discovery of ferrocene and its many analogues. The field remains a highly topical one to this day, and there are numerous important applications of organometallic complexes, such as catalysts in the polymer and pharmaceuticals industries. Recall that strong field ligands such as carbonyl engage in pi back bonding interactions with metal centres in low oxidation states. The carbonyl ligand has a filled highest occupied molecular orbital which is predominantly based on its carbon atom, and this can be donated into empty metal d orbitals of appropriate symmetry in what we call a sigma bonding style interaction. From the molecular orbital diagram for carbonyl, we can also see that the ligand has empty pi star antibonding orbitals. These are the lowest unoccupied molecular orbitals, which can accept electron density from the metal centre in a pi back bonding interaction. Sigma donation has the effect of strengthening the metal-carbon bond, while pi back donation has the effect of both strengthening the metal-carbon bond and weakening the carbon-oxygen bond. These interactions are synergistic, so they happen together. Unlike coordination compounds, organometallic compounds have relatively few stable electron configurations. In fact, organometallic complexes with strong field ligands usually have 18 valent shell electrons around the metal atom. The 18 electron rule states that a stable complex with the electron configuration of the next highest noble gas is obtained when the sum of the metal d electrons, electrons donated from the ligands, and of the overall charge of the complex equals 18. So we can use this rule to predict the stability of organometallic complexes, but first we need to actually learn how to use the 18 electron rule. We can do this in steps. First, the number of d electrons needs to be determined. This is obtained by looking up the element in the periodic table and determining its group number. Once the group number is known, subtract the oxidation state of the metal. So for example, iron 2+, iron is a group 8 element, so 8 minus 2 is 6 electrons. Next, the number of electrons donated by the ligand needs to be determined. In many cases this is straightforward, but for some organic fragments it's not entirely obvious. In general, alkyl, alkenyl, aryl, hydride, amide, alkoxide and halides donate 2 electrons and bond to the metal as anionic sigma donor ligands. Similarly, pi acceptor or pi acid ligands such as carbonyl, isonitriles, phosphines, dinitrogen and alkenes can donate 2 electrons to the metal as neutral species. Even nitrosyl is a cationic 2-electron donor. So let's do some examples. Here's an iridium complex. First we need to count the electrons contributed by each of the ligands. The triphenylphosphine, carbonyl, methanide anion, chloride and iodide ligands are all counted as being 2-electron donors. Remember that this is our counting convention, even though the methanide, chloride and iodide are all monoanionic ligands. Secondly, let's consider the iridium. First, we work out its oxidation state. There are 3 monoanionic ligands and 3 neutral ligands coordinated to the metal centre. So given that the complex is neutral, the iridium must be in a 3+ oxidation state. The number of valence electrons is the group number, iridium is in group 9, minus the oxidation state of +3. So we have 6 d electrons for the iridium 3+. We therefore count 18 electrons overall. So this is a stable 18 electron organometallic complex. Here's a molybdenum complex where all the ligands are neutral this time. Each of the 6 ligands is counted as being a 2 electron donor. The complex is neutral overall, so the molybdenum must have an oxidation state of 0. Since molybdenum is in group 6, the number of d electrons is simply 6. So in this particular example, the total electron count is 18, and this is a stable organometallic complex. The examples given here are for relatively simple coordination geometries. However, we'll see in lectures that there are some very interesting geometries for organometallic complexes, which include sandwich complexes, piano stool complexes, and even side-on bonding of certain ligands. In lectures, we'll also see that square planar organometallic complexes often obey the 16 electron rule. The quiz that follows will test your ability to understand these concepts that we've discussed here. That concludes our pre-lecture video for this week. Good luck, and we look forward to seeing you in lectures.